Follow-up video, and I am not quite as organized as I would like to be, but honestly, it's 7:19 a.m. right now on Tuesday morning, and I have to leave the house at about 9 a.m. So this is the time we've got. So that's what we're gonna do. So I'm actually gonna pick up kind of where we left off. So this question was asking about experiments like the oil drop, things like that. So first of all, if you haven't seen those are hanging out in the 701 section. There's pre-recorded lecture videos, and in chapter 2, please go through. There are some that talk about different experiments. Those are really there to give you guys an idea of where the subatomic particles come from. And so what you need out of all of that really is just have a general idea that things like electrons are negative, and that the nucleus is dense, and is roughly in the center of the atom. So like, for example, one of the things when we were drawing orbitals, I just kind of drew them and I put them and they were on axes. And so we're going to call this a py orbital, and we'll pretend that that's symmetrical. One of the things that I actually left out from the review last time is that we're assuming that there's a nucleus in the middle. So we're assuming that there's protons and neutrons hanging out there in the middle. Anytime that we talk about atoms, we have a tendency to get caught up in the electrons because the electrons are more mobile. But those protons define the element, like they still have a lot of importance in there. So we don't emphasize the experiments a lot, but they are still good to know, especially because it's nice to know where things come from and how we know what we know, and that's what that's for. This question was about valence electrons, specifically calculating the valence electrons for transition metals. So I have to admit, I really thought last night that I had already done that, but I'll go ahead and do another example because now that we've done, because I'm basically, as I do this video, I am assuming that you went ahead and already watched the first video, or that you have a general idea of some topics, because I'm going to assume that you already know that we have exceptions to the electron configuration. So let's do two different examples for transition metals and valence electrons. So let's go ahead and do chromium as one of those, and we'll also go ahead and do iron. So we're going to do two examples. So we're going to go ahead and do iron first. So when we're talking about iron, I'm just going to start off with the noble gas shortcut. So there's argon, and then I'm at 4s2, and then iron is 1, 2, 3, 4, 5, 6. So I'm in the 3D subshell, and there's 6 electrons in the 3D. If I was to write this out with just looking at everything past the noble gas configuration, it would look like this for iron: 1, 2, 3, 4, 5, 6. That electron's supposed to be, actually, just move that over still a little. Fine, I'll just erase you and redraw you. Sorry, that electron looked like it wasn't actually on the line, and that's bothering me. There we go. So that's iron. When we're talking about looking at valence electrons, I'm looking for the highest value of N. So if I want valence electrons, I need the highest value of N. And so I've got two values of N shown. I have 4 and I have 3. 4 is greater than 3. These are the valence electrons. These are the only valence electrons. So as far as number of valence electrons for iron, the answer is 2, and just 2. Just 2 valence electrons for iron. when I go to chromium. Now, chromium is going to be a little bit different. So even though we can still think about this and we're tempted to do that whole 4s2, chromium is one of the exceptions. So this is actually 4s1, 3d5, and I can draw that out. But this is that idea that having a half-filled subshell is more stable, and therefore you're going to have 5 electrons in the 3D, and that is more favorable than having than following the Aufbau principle. So we are still looking for the highest value of n. I still have 2 values of n. I still have 4 and 3. So 4 is where all of my valence electrons are coming from. And for chromium, then I only have 1. I don't know if you guys can actually see that one valence electron for chromium. So you're always looking for the highest value of n, and in transition metals, that means you have either 1 or 2 valence electrons, depending on if we asked you about an exception or about one that follows the rules. So hope that one helps. I'm recording, right? I am recording. Yay! Okay, so we talked about the experiments and we talked about valence electrons. Yes, I am drinking coffee, in case you wondered. Okay, we did the exceptions. Yay! We did the exceptions. I got asked about a couple of times. We have talked about valence electrons. So I'm on quantum numbers, ionization energy, and techniques to go from grams to moles to atoms. Let's go ahead and do the technique. We'll do this one first, and then I'll figure it out. Probably ionization energy, and then probably quantum numbers. And then miscellaneous stuff from my classes, because I had a couple of questions in there that I definitely want to touch on. Anyway, so techniques to go from grams to moles to atoms. So, and especially how you know. So we're going to go ahead and we'll start with grams. So, and where's an element? This guy. I've never used this one before. So let's go with 10 grams of CE, cerium. And the goal, we do want to go to moles. Actually, we'll go ahead and just say the goal is to go to atoms. Goal is to go to atoms. So what I'm going to do through this is I'm going to show you where all the numbers come from, but I'm also going to show you a logic step that I use to make sure I went the right direction. Because there are some tricks. There are some things that are actually always true. And you can use those to figure out if you've gone the right direction. And I think that's what this person was asking for when they were like, all right, what's the trick? I'm like, to me, there actually is a trick. Because there is some stuff that you should be able to know just by looking at the numbers. Okay, so the goal is to get to atoms. So one of the things that I actually know, and this is one of the tricks, one of the things that I know is that if I'm ending in atoms, this has to be a large number. This has to be a large number. Atoms are incredibly small. So not only does it have to be a whole number, this has to be a big number. Like the smallest number this could possibly be is like 1,000 or 10,000. This has to be so big, y'all, so big. So even if we take some of the more massive atoms that have a lot of like heft to them and they have a lot of mass, you still have to have multiple atoms. So I don't care how big or how small that gram number is. You have to, when you end in atoms, that number's got to be big. You've either got to have a big exponent on there, something like big, big number. So either big positive scientific notation exponent or something, but big number. So when we're done, I expect a big number. So if this is a multiple choice question, usually we bank on people forgetting if you multiply or divide. And so we'll have some stuff in there with negative scientific notation. And that's like a piece of an atom. And that's just not a thing. That's just not, we don't do partial atoms in this class. No, whole numbers, big numbers, atoms, big. So that's the first thing. The other thing to know is that if you start off with grams, you are going to the periodic table. So if grams is where you begin, you need the periodic table. If you were starting with moles, probably not. But if you've got grams, well, we'll talk about that. But you need the periodic table if you have grams. There's no other way to deal with it. Yeah, I know we've got atoms, so yeah, we're going to use some other stuff, but you have grams. The only way to get out of grams, because you actually deal with this thing, you got to deal with the symbol. We probably also gave you something like the Z number, just because if you have to spend time on the exam looking through every single element, this can be time consuming. So we'll often try to give you some sort of information. And so giving you the Z number is a thing that we'll sometimes do to help you out. So the thing though is that I can't go directly from grams to atoms. Um, so that's not a thing we're going to do. So we are going to go from grams to moles to atoms. And one of the things you're going to see in this course a lot is we go to moles often. So moles is a unit that we are often in. The mole is like saying a dozen. So moles are just a way to talk about an amount of atoms. That's a whole bunch of them all in one place. So for example, I don't actually have an egg carton with me, but usually I do. Anyway, I've got a little bag here. I'll get rid of this. I have a bag here of treats, right? So these are the dog treats I leave on my desk for my dog. And I don't know on this packaging, it does give it to me in like a weight, but I would just refer to this as a bag of treats because I don't actually know how many are in here. Yeah, he's eaten a lot of them. But even when I bought this, right, I would have just said like, go get me a bag of treats. And I'm counting on this bag of treats being a fairly good number. And yeah, we could say that this is like 50 to make our lives easier. That when it was new and when it was fresh, that this was a bag of 50 treats. So when I say a bag of treats, I actually mean 50 of these little tiny things. But we're not going to count them individually unless we really care. And so when I say, hey, go get the bag of treats, the bag of treats actually has 50 inside of it. That's basically what we're doing when we say moles. When we say moles, we're just saying, hey, a group of atoms. The size of our group is a lot larger, but that's why we use the mole, is so that we can just talk about it as a group. Have I brushed my hair this morning yet? No. But did I leave my camera on so that I could gesture at things? Yes. Okay, so I am going to go from grams to moles because I need to be able to talk about a group of things so that I can get to atoms. So because I need to get from grams to moles, and I point out the fact that since we have grams, we're going to need that periodic table. That means we actually want, I know it's kind of small in here, but the number underneath, the small number underneath. So it's 140.1. So from the periodic table, we are going to use this number, and it just says 140.1. You need to know that this is the number of grams in 1 mole. That's what that number means. You can also have that number represented as 140.1 AMUs in 1 atom. That is another option. But that's the other thing that it can mean, is 140.1 AMUs in 1 atom. But otherwise, we usually use this as 140.1 grams in 1 mole. So now I'm going to get rid of the grams. So the way I'm going to do this is the way that we were talking about it with trying to get rid of my units. So since I don't want grams anymore, I'm going to put grams on the bottom. That's all slanty. That's just going to be slanty. So I want to make grams go away. So I need grams to be the opposite place. So I've got grams on the top for the 10. Grams are going to go on the bottom here. So I'm going to take that ratio that I have in blue and 140.1 grams in 1 mole. Now, one of the other things I want you to notice, yeah, the calculator. Uh, divided by 140.1. So this is 7.138 times 10 to the negative 2 moles, or your calculator might have also spit out the fact that this is 0.07138 moles. Same number, same number. So whichever one you got, doesn't matter. So one of the things I want you to notice is when I went from grams to moles, the grams is the bigger number, the moles are this is the smaller number. It wasn't super drastic, right? Like I went from 10 to 0.07. So I did wind up using scientific notation because my calculator is stuck in scientific notation. But that's all that happens. So I did have a change. It was a relatively small change, but my grams are bigger than my moles. That is always true. The gram number is always bigger than the mole number. That's the other way that you know you went in the right direction. How do I know that? How do I know that the gram number is always bigger than the mole number? The periodic table. That's how I know. So I don't care where you are on here. We can look at mercury down here at number 80, which says that there's 200 grams in a mole. So if I was doing that saying like 10 grams, how many moles do I have? I would have divided by 200, get smaller. The lightest element we have is hydrogen, and even that's not one. It's 1.008. So just to demonstrate, if I had those 10 grams of hydrogen, I would have divided by 1.008 grams in 1 mole. And this is the lightest element we have. So if I was going to have anything that got me the biggest number of moles for the number of grams I have, this is 9.92 moles of hydrogen. So the lightest element, the thing that will get you the most moles for the amount, still gets you fewer moles. The number of moles is smaller. The number of moles is smaller than the number of grams, and that is always true. To go back to my treats analogy, I would need different treats. So these are pretty small, right? These are pretty small. They have a relatively small mass. So since these actually are done by mass, right? I don't know if you can see this, but this originally was 6 ounces or 170 grams. So the number of treats that I could get in this bag, and the size of the bag is relatively small because my treats are small. So one bag, 50 treats, but also if I'm talking about this having to be 6 ounces, got lots of treats in there. If I was still using 60 ounces, or 6 ounces, whatever the number is, if I'm using the same mass, but I have a bigger treat, this is actually a squishy toy, but anyway, if this then is my treat, this is bigger. This actually does also have more mass. I know you can't feel it. But if I'm trying to compare one of these little things and one of these, and a bag is 50, I need more mass to get there. So the mass matters when you talk about moles. So the mass matters when you go from grams to moles. That's what I mean. The mass matters when you go from grams to moles. Because essentially, if I've got 6 ounces, these are really light. I can get a lot of treats for 6 ounces. These are pretty heavy. If I'm still doing 6 ounces, I can get more than one, but not nearly as many because of how hefty they are. So if I'm talking about mass, the gram amount, you'll get more physical items for the same mass if the item is lighter. There. Should definitely plan some of these analogies in advance. Okay. Have I solved the problem yet? No. So the goal is to go from 10 grams of cerium to atoms of cerium. We have gone ahead and gone from my 10 grams to moles, noting that my gram number was 10, my mole number is 0.07 stuff. So my mole number is smaller. Now I'm going to go to atoms. So this is where I do need one more number. And I need the number off of my potentially useful information. So on the potentially useful information, there is this thing called Avogadro's number. And that is what I'm looking for. So Avogadro's number is the thing that's going to let me go from moles to atoms. So I have moles. Yay, moles. And then I'm going to go from moles to atoms. We already commented that that atom number needs to be big. The atom number needs to be big. So while yes, I am going to go ahead and show this off with the math, you perhaps already are thinking, well, if I need it to be big, I multiply, right? You do. Make the number be big. So this is my number of moles. And then what we do go ahead and say so that everything cancels is that in 1 mole, I have 6.022 times 10 to the 23rd atoms. So that's how the actual math works out. But again, as far as tricks go, the trick is atoms have to be big. You have to have a large number of atoms. There's a bunch of them all in one place. So your atom number needs to be large. So if you're solving for atoms, that final number needs to be a big number. 4.3 times 10 to the 22nd, big number. So again, thinking about outside of scientific notation, 4, 3, 1, 6, 9, 12, 15, 21. Oh, 24, whoopsies. Too many zeros, that many zeros. Great. Da, 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 da. I don't even know what this number is. But it's a lot. Lots and lots of zeros. Lots and lots of atoms. So those are my tricks for remembering what to do. If you start off in grams, so summary. If you start off in grams, you need the periodic table. It's the only way to go anywhere. If you start with grams, you have to have a periodic table. If you know you're ending in atoms, you know it's a big number. Depending on where you're going, if you're going between grams and moles, your gram number should be bigger than your mole number. Gram number should be bigger than your mole number. Doesn't matter which direction you go. If you start off with moles and you go to grams, then the mole number should be smaller than the gram number, no matter which direction that takes you. So the mole number is smaller, the gram number is bigger. The atom number should be big, positive exponents, big. So hopefully that helps with grams to moles conversions. Technique. Boom. Ionization energy. Yay. So ionization energy has, I think this is 3 parts. It has a definition. It has ionization. I'm just call it ionization energy 1, ionization energy 2, ionization energy 3. So I'm just going to call it. And then it has exceptions. So ionization energy has 3 parts that we're going to talk about. I'm going to grab my slides for this because I want where's ionization? This. So ionization energy is the energy required to remove an electron from an atom in the gas phase. Why is it the gas phase? I'm going to have subtitles. Okay. But this is a Teams video, already has subtitles. Energy required to remove an electron from an atom in the gas phase. The gas phase. It has to be the gas phase because 1, we are still in individual atoms. So no matter how much you like it or dislike it. These are individual atoms. And this is not what happens when you put sodium in water. That's different. So this is just what happens when you have sodium atoms heated, because that's the only way you're going to get them to be a gas. But what happens when you have sodium atoms all by themselves? So the goal is to think about atoms alone, atoms by themselves, not interacting with other things. So I know for some of y'all, you're very excited about like compounds and molecules and reactions. We're not there yet. So these are atoms by themselves. The way we talk about atoms by themselves is the gas phase. This is also ionization energy. We are removing electrons. So that's the other thing to remember. We are removing electrons. So in general, this is easier to do when you have larger atoms. So I did skip atomic radius. But ionization energy is lower, so that's the highlighted part. So you have lower ionization energy the farther you are to the left on the periodic table. You have lower ionization energy the lower you are on the periodic table. Part of the reason for this, now I need to draw something. Um, Part of the reason for this is because if I'm thinking about things that have just that lovely n equals 1, and I've got 2 electrons in n equals 1, those are pretty close to the nucleus. The farther away you are, 1, 2, 3, 4, that's n equals 4. So if I'm trying to remove an electron that's close to the nucleus versus an electron that is far away from the nucleus, this one that is in n equals 4 is farther away from the nucleus. It is easier to remove it. So easier to remove farther away from nucleus. So when we say easier to remove means less energy needed. Less energy needed means lower ionization energy. So that's how that logic works. The physically farther away the electron is from the nucleus, the less energy you need to pull it away. The less energy you need is a lower ionization energy. So that's how ionization energy works in general. So that's why the larger the atom, the lower the ionization energy. The smaller the atom, the higher the ionization energy. When we talk about, oh, I need successive, we'll do this. So this is a graph that looks at ionization energies, and what you might notice is that overall, as you go across a periodic table, it does go up, which is what you would expect. So that overall ionization energy increases across. But there's places where that's not true. So you can kind of see in here, there's some areas where it goes up, but then it goes back down just a little bit. That is the half-filled subshell thing again, but this time in the P block. So I'm going to put this on top of a periodic table so we can look at both things at the same time. Periodic table, I want to be over here. Boop. Hey, hey. Okay. So when we are talking about this notion of harder to remove and easier to remove, for ionization energy in general, we're expecting that to just increase across. But when we're looking at group 5A, these are actually harder to remove because I have a beautiful half-filled subshell. Beautiful half-filled subshell. It is lovely. It is so incredibly stable. It does not want to change. So we're going to make that just a little bit bigger. There we go. So everything group 5A is actually a little bit harder to remove. So it's got a little bit of a higher ionization energy. My group 6A then next door is actually a little bit easier to remove. So instead of this going directly across, that means 5A is a little higher and 6A is a little bit lower. So in ionization energy, when we're expecting this trend to just go up and up and up and up and up, it doesn't. It goes up for boron and up for carbon and up for nitrogen and then down for oxygen, and then up for fluorine and up for neon. So this little jig jag here is because we're going to go back down and the ionization energy of oxygen is lower than that of nitrogen, because if oxygen got rid of one of its electrons, it actually is a half-filled subshell, and the whole half-filled subshell thing is great, more stable. It's lovely. So oxygen's kind of ready and willing to dump one of its electrons for the sake of having a half-filled subshell. Whereas nitrogen is already there, it doesn't want to give it up. So nitrogen's has a little higher ionization energy than you might expect. Oxygen has a little lower ionization energy than you might expect. So those are the exceptions we usually look at, are in that half-filled p subshell. Now you can see it shows up in other places, so it's not like that's the only place where it happens. But dealing with group 5A and 6A is where we typically talk about it, because it emphasizes the half-filled subshell, which is also something that we talked about when we did the exceptions to electron configuration. But again, there are other places where it shows up, but that's where we have a tendency to emphasize it because of that fact. The other thing, the reason why I'm circling these, you might notice it's not a big difference. It's there, it's measurable, it is a difference, but it is not big. So it is there. We do ask you guys to know about it because, again, we're emphasizing the stability that comes with half-filled subshells. But also do note that it doesn't go like all the way back down to the x-axis. It's not that big. There's a third thing in in ionization energy. It's successive ionization energies. So when we talk about everything we talked about so far is what I think of as first ionization energies, which is removing the first electron. So if we're doing sodium, we start off with a neutral sodium atom in the gas phase. And as we go to the first ionization energy, we go to a sodium positive, still in the gas phase, plus an electron. We removed an electron. When we then want to go to the second ionization energy, we pick up where we left off. So we remove a second electron. And this is important because we're going to basically start where we left off. We start with this thing. So we actually start with that positive sodium ion, still in the gas phase, and then we remove another electron. We remove a second electron, but we remove them one at a time. So when we talk about first ionization energy, second, third, fourth, we are still removing them one at a time. We remove them individually. And that's important because when you get into ALEX, for example, it's going to have a little graph, and it's going to do things like ionization energy 1, ionization energy 2, ionization energy 3. We'll go ahead and do an ionization energy 4, and we'll make my x-axis a little longer. Y-axis is energy, and I just have to make little bar graphs. And this is going to be for sodium. I'm sorry, these bars are not all the same size. So two things. One, each ionization energy goes up, gets higher. It's harder to remove electrons as you go. Essentially, even after the first one, removing that first one it might be easy, might be hard, but removing the second one, that poor little nucleus is hanging on to its electrons as hard as it possibly can. You took one away. Maybe you took two away. It doesn't like it. So the positive nucleus also then has the more electrons you remove, the fewer negative things that positive nucleus has to hang on to. So it usually is more effective. So that positive nucleus is more effective at hanging on to electrons, the fewer electrons it has. So it gets harder to remove them as you go, requires more energy. Second, look at this difference. I don't know if you can see that. That's yellow. Let's use a different highlighter color. We'll just use pink. Look at this difference in here. Look at the difference. Look at this difference in between my bars. So as I'm going in, maybe I should have used this. Anyway, doesn't matter. Moving forward. So anyway, so there's this difference in between my bars. There's this difference in between my bars. There's this difference in between my bars. What I hope you can see is that the gap in between 1 and 2 is the biggest. That means that the small bar is a valence electron. And my big bars over here are what we refer to as core electrons. What that means is for sodium, periodic table. I need so many of these. For sodium. Sodium's hanging out here, group 3, or sorry, period 3, 1, 2, 3, group 1A. So period 3, group 1A. So for sodium, if I was to do the notation for that, 1s, and I'll make this go up a little bit, 2s, 2p, 1, 2, 3, 4, 5, 6. Uh-oh. Yay, 3s. I can get it all on one page. 3s, 1. So when we talk about this first ionization energy, that first ionization energy, we are in fact removing this electron. And notice it's the only thing in n equals 3. It's the only thing that has that n equals 3 part to it. So this was the valence electron of sodium. Everything else in the sodium atom has a smaller value of n than that first electron. So for sodium, that very first valence electron is easier to remove. All of the core electrons with all the core electrons with a lower value of n are more difficult to remove, and you can actually see that reflected in the graph. So typically what I like to do on the Alex question, which sometimes we also write as an exam question, is I like to just count the little bars, because basically every little bar is a valence electron. So for example, in Alex, it'll say something like, here is a graph of successive ionization energies, first, second, third. What will just be fancy and do a period 4 element is this. Actually, I lied. Wait, I lied. I don't want period 4. I lied. I want period 2. I want period 2. That's what I want. I want period 2 element is this. So all I'm going to do is I'm going to say, aha, I have 2 valence electrons. The rest of them are core. Since I have 2 valence electrons, I want period 2 with 2 valence electrons. Period 2, it's right here. 2 valence electrons is this guy. This is beryllium. And I am done. In case you wondered, the reason why I suddenly panicked and was like, not period 4, not period 4, is because I started off this video talking about how most of the transition metals have 2 valence electrons. So I did not want to go back into how do we know that it's not a transition metal. It's period 2, it's not a transition metal. This is also way easier, by the way, as a multiple choice question, because then you can control all 5 answer choices and you don't have this issue of the entire periodic table being options. So that's ionization energy. What else am I doing? So I think those were the three things. Quantum numbers. This also works out well doing quantum numbers because that was definitely a thing that a lot of the students that I asked on Friday also want to talk about was quantum numbers. We'll likely talk about those until my voice is completely gone. Yay! Okay, so first thing I'm going to mention is if you would just like to hear things again. Grant, I know this is being recorded, but in the 701 section, we do have pre-recorded lecture videos, and hanging out in the chapter 3 stuff should be stuff on quantum numbers. I know these aren't labeled with the topic, but you should be able to find them in there somewhere. So if you just want to listen to somebody else, I think these are done by Dr. Diekman. I know they have my name on it, but I think those are Dr. Diekman's videos. So for quantum numbers, one of the things I'm also going to rely on is, so I'm going to talk predominantly about quantum numbers and how you figure out both electrons, and how you figure out some of the connections between them. I will probably forget some stuff as I go along. So just keep that in mind that you still want to go back over your notes, even though I'm going to go through all of this. So I'm just going to start with n equals, so we'll start with n equals 1. So whenever we talk about n, this is what we refer to as the principal quantum number n. N is the same n as when we were doing Bohr orbits. This is the energy level. This is a big deal. This is also hanging out on the periodic table. So these little numbers are values of n. So you see n actually shows up a lot when we've been doing orbital notation. This number 1 is a value of n. That number 2 is a value of n. So n is just a counting number, and it starts at 1 and it goes to infinity. So even though for the periodic table, we pretty much only need to go to like 7, because we can have excited states, your n technically goes all the way to infinity. So, but we're talking about a particular energy level when we talk about n. So when we talk about L is usually when things start to get complicated, is n starts at 0 and it goes to n minus 1. But the thing is, when we say that, L is also our subshell. N, by the way, is our shell. So the tricky thing here is when n is equal to 1, L is equal to 0, and that's all we have. But if n is equal to something like 3, then L is equal to 0, and L is equal to 1, and L is equal to 2. So when we talk about this, the n equals 3 shell has 3 subshells, and all of those exist. So whether or not there are electrons in all of them is another story. But once you have the n equals 3 shell, you have 3 different subshells. L is equal to 0, L is equal to 1, and L is equal to 2. And they all exist. Again, whether or not they're all filled with electrons, different, but they all exist. So as we move up, so basically, so when I wrote 2s, I'm going to go ahead and write 2p up here. So my 2 is my value of n. This letter is my value of L. And when we say S, that's an L equal to 0. So S is an L equal to 0. P is an L equal to 1. L equals to 2 is D. Now, it was in the exam review video, but I'll mention it here real quick, that also means that subshells could have shapes. So we could also do a sphere. We could also do the dumbbell shape. We could also do the cloverleaf shape. That's a cloverleaf. Or we could do the thing with a donut. So L relates to shape to subshell. And again, for L, the highest value of L is 1 minus, is in minus 1. So the highest value of L is in minus 1, not in equals 1. In minus 1. Can I get my eraser? There we go. Every once in a while, I'm like, ah, yes, the tablet in the classroom is more expensive than the tablet I have at home. It works better. So the highest value of L for any particular shell is equal to the shell number minus 1. So there's lots of different ways to say that, to look at that, but that's what we're talking about here. Then IMSL. So for every value of L, we can talk about IMSABEL. IMSABEL goes from negative L to 0 to positive L. So when L is equal to 0, IMSABEL is just 0 because there is no positive and negative 0. So if L is equal to 0, IMSABEL is just 0. That's all you got. IMSABEL gives you the orbitals. The orbitals are those lines we were drawing. So the fact that I only have one line right here, that's my IMSABEL equal to 0 because my L is equal to 0. I have one line here, that's IMSABEL equal to 0. But I have 3 lines here, L is equal to 1. That's my IMSABEL is equal to negative 1 and 0 and positive 1. So I can talk about my values of IMSABEL, and I should have basically one orbital dash for each value of IMSABEL. For the sake of showing this off, we're going to go ahead and also do the 3. Actually, I'm going to go ahead and stick the 4s in here because this is where it goes. 1, 2, 3, 4, 5. This is the 3D. And since that's the 3D, my values of IMSABEL, and so the 3 is my value of N, the D is my L equal to 2, which means my IMSABEL values start at negative L, negative 2, negative 1, 0, positive 1, positive 2. That's 5 values, negative 2, negative 1, 0, positive 1, positive 2. So that orbital notation comes from quantum numbers. That's where it comes from. The last quantum number is m sub s. M sub s only has 2 options. It's either positive 1/2 or negative 1/2, which is why we draw arrows that are up and down. So these we would just pretend are all positive 1/2. So when I say we pretend, what I mean by that is because the arrows are just a convention. It's basically, when I say it's a convention, I basically mean it's like we use them, but we don't actually have an official up arrow means positive 1/2. Now, because I personally think of up and positive as going together, that's what I usually think of. So usually if I say, hey, draw me something with a positive 1/2, I usually do an up arrow, but it doesn't really matter. What matters is they're equal and opposite. So if I want to, I could actually go ahead and just draw a down arrow and be like, that has positive 1/2 because I said so. And that's fine as long as the arrow is half. Spin has to be positive 1/2 or negative 1/2. spin is not a whole number, but it can be negative. So whether spin is up or down, whether spin is positive 1/2 or negative 1/2, it doesn't matter. So whether spin is positive 1/2 or negative 1/2, it doesn't matter. Either one is fine. Sorry, I just saw my light is blinking for some reason, and I don't like that. I wonder what's wrong. Nobody else is home but me. It's possible I'm losing internet, which would be very sad. Hopefully not. But I am on Wi-Fi. Well, just gonna cross our fingers. So that's quantum numbers in a nutshell, as far as what's going on. Now, one of the things that this does mean, so we have a tendency to do things like which is not an allowed set of quantum numbers. And when we do sets of quantum numbers, we always do them in L, M sub L, M sub S. So if we want something that's not an allowed set of quantum numbers, we'd give you like two sets to pick from. Something like this. And we'll just do one more. So whenever I'm looking for things that are not allowed, I like to double check M sub S first, just because if that's not positive or negative 1/2, then it's wrong. But those are both fine. Those are both positive 1/2. Then you actually have to go through the set. So this is n of 2, and when n equals 2, I have two options for L. I have an L of 0 or an L of 1. So n is fine, L is fine. M sub L has to be based on L. When L is 0, M sub L has to be 0, so that's fine. So this one's good. It means this one should be wrong. N is equal to 2. I have two options. I have L of 0 and I have L of 1, so that's fine, and L is fine. But when L is equal to 1, my options for M sub L are -1, 0, and +1, so this 2 does not work. So that's basically how that one works. And you do usually just have to go through them all. Again, I like to start with spin, because oftentimes if spin is what's wrong, spin only has two options. You can find spin pretty fast. The other ones you just have to go through. One of the other things we can go ahead and do, so since I have it here, we'll go ahead and we'll also just give the quantum numbers for this particular electron. So as I have actually all the information I need, and I'll show you one thing with it. So I know for this particular electron that I have an n equals 3. Because of the S, I know that L equals 0. Because L is equal to 0, I know M sub L also has to be 0. Then M sub S, you have two options. So again, you can do positive 1/2. That's fine. You could also have told me that all of these other ones are the same, and M sub S is equal to -1/2, and they are both correct because there's only one electron in there. I don't have any information about anything else, so it's either positive 1/2 or negative 1/2, and both of those would be correct. So when you have, so as long as all of your options work out, it's fine. So similarly, I'll give you another example that makes people mad at me. If I do this electron here in the 2p, N has to be 2, L has to be 1, but then my M sub L value, I have 3 options and they're all correct. So that could be the positive 1 for M sub L, and then I've got 2 options for M sub S. So there are actually 6 different sets of quantum numbers that would be counted as correct if I'm just pointing at this electron. This is the thing. If this is a short answer question, then there are 6 answers that are correct. N has to be 2, L has to be 1, but M sub L could be positive 1/2 or 0 or -1, and M sub S could be -1/2 or positive 1/2. And any of those answers have to be correct because you don't have any other information. And it's convention. And that makes people mad. If it's a multiple choice question, then we'll only give you one of those options. And we'll screw around with N values and L values. Or we'll have things that are not allowed, or we'll ask you if M sub S is 0. So realize that we are not going to let you pick between two answers that are both correct. I don't know if you've thought about this, but I have, because I've been writing Gen Chem questions for a really long time. We only have 5 answer choices. That means that I want those answer choices to be good. I don't want you to be able to pick between two things that are both correct. They're both correct. I only get 5 answer choices. I am absolutely going to spend my other 4 answer choices giving you things that look good but are wrong. I want to make that challenging. I don't want to make you pick between two things that are right. I want to make you pick between things that are wrong, and one of them is correct. So while there are multiple options, if it's short answer, then if there's multiple options that are correct, they'll all be counted correct. If it's multiple choice, then there's only going to be one correct answer. We have 5 people writing the exams this year. All 5 of us are looking at all of the answer choices to make sure there's only one correct answer. 8:15. What else do I got? That's quantum numbers. Now I'm going to go take a look at what my class asked. And also, did I make it through all the questions? No. Sorry, when the little arrow starts to do that, that means Teams got mad at me. I don't like it when Teams is mad at me. I have to X out of Teams real quick. Hold on. Or I have to X out of OneNote. Music comes back. It's okay. Great. Okay. We did electron configuration. Right? Did we do electron configuration in the exam review? Did I skip electron configuration? No, I did some electron configuration. Oh, that was quantum numbers. I think I did electron configuration. If I forgot to do electron configuration, you have my most sincere apologies. So electron configuration, just in case I missed it. We start at the top. So, and actually you saw me do some of that with the other notation. So for electron configuration, this is the part where what I was actually doing is I was actually doing orbital notation. So this 1s, so this is 1, this block here, I did this yesterday, is S. This block over here, I'm going to try to avoid helium, is P. This block in the middle is D. This block down here is F. One of the weird things about this is dealing with the D block. So I'm going to go ahead and go high enough to hit the D block. So 1s, and you might notice there's only hydrogen and helium up at the very tippy top. So there's only 2 electrons that go in the 1s. There's only 2 electrons that ever go in S, and that is because of quantum numbers. And then when we hit 2p, there's 6 electrons that belong there, again, because you've got 3 orbitals for 3 values of M sub L. 3s, 3p. Now, this is the part where it's worth looking back at where we were. So this is 3p here. But for quantum numbers, it's tempting to go to 3D, but we don't actually go to 3D yet. We actually go back and we go to 4s first. But because of quantum numbers, when we do hit D, this is actually the 3D. This is the 4D. This is the 5D. This down here is the 6D. This down here is the 4F. So I would then go to, after 3P, I'd go to 4S, and then I'd go to 3D. So I'll get to 3D, but I only get to 3D after the 4S as we fill in electrons. So that is something to keep in mind, is how those work. The other thing, I just didn't like mercury, because the other thing that is true is that we don't land you in the F block because there's too many exceptions in the F block, but we'll land you outside the F block. So like golds. Gold is one of the exceptions. But we can absolutely do the electron configuration for golds. So we would start with the noble gas because otherwise that's a heck of a lot of stuff to write out. Xenon, and I start back over here on my far left. So I'm at 6s. This is gold. So this is actually 6s1. It's one of the exceptions. And then before I forget, I'm going to go ahead. Says 57. This says 58. So I am in fact in 4F, and that is 14. And then I come back and I'm in 5D10. So gold is one of the exceptions. That's why I've got the S1. And then we're not going to land you in the F block because there's more exceptions than there are. Okay, I think I actually did that during the exam review. But hey, we did it again. That's why I'm supposed to check them off when I do them so that I remember I'm done. Okay, so some things from my class. Why does gold have 2 valence electrons and not 8? Gold actually has 1 valence electron due to highest value of N. I was lucky. Let's go back to that electron configuration. Oh no, can't I find it again? Oh, one note. Where did we go? There it is. So, so one of the questions asked was about the number of valence electrons of golds. For the purposes of this class, we would actually tell you that gold has 1 valence electron. Because whenever we're looking for valence electrons, we're always looking for the highest value of N. So this is N equals 6. That's the highest value of N, and there's only 1 electron. 1 valence electron for gold. In Alex homework for module 2, I saw a question asking how many lines are in the absorption line spectrum using the energy diagram. I don't know how to find the right answer. So that question looks something like this. Had some lines, and then the question is how many lines are in the absorption spectrum. So you're actually supposed to count how many different ways can you go in between the lines. What I mean by that is, if I have an electron, so this is absorption spectrum, so we go up. So if I have an electron in the ground state, it can go all the way up to the top and land here. If I have, or it could have landed there. If it did land here, it could also go ahead and jump up here. So I'm looking at how many different options do I have in between lines. When I've got 3 energy levels, I have 3 lines. If you had one that had 4, let's see if I can do 4. I will not, part of my brain is like, let's do 6. Actually, I'll do 5 real quick. Why not? So all we're going to do is look at all of the options. So I start at the bottom and I go to the top. So that's 1. I start at the bottom and I go to the next one, and that's 2. I'm just counting. I'm just writing the numbers down so that I'm counting. 4. But then I also have to start at the second level and go to the top. That's 5. And start at the second level and go not all the way to the top, and that's 6. 7. Because basically each one of these should be a different absorption line. So every single line that I'm drawing should relate to a different energy. So that 1, 2, 3, 4 all starts in the ground state and gets excited up. But those are all different energies from the others. I know when I drew the lines, they're kind of looks like they all have the same gap in between them. Sorry about that. I could keep going. 1, 2, and then the very last one. So I've got 8, 9, 10. So I had 1, 2, 3, 4, 5 lines. I had 10 transitions possible. So I had 3 lines. I had 3 possible transitions. I had 5 lines. I had 10 transitions possible. And that's really is how you do it, by the way, is you just double check to make sure you've got all the possible transitions in between lines. Each possible transition relates to one line on the absorption spectrum or on the emission spectrum. Absorption means you go from low to high energy, which is energy in. Emission is the opposite. Emission spectrum is going to be that energy out. You go from a high energy to a low energy. Energy goes out. So absorption, energy in, emission, energy out. Okay, so I talked about this one. I talked about this one. In class, we learned that L keeps going, essentially. So that when you have L and you go 0, 1, 2, 3, you can keep going 4, 5, 6. So that's S, P, D, F, G, H, I. Keeps going. Do they have blocks on the periodic table the same way the rest of the shapes do? No. And do we always get to see those shapes if n equals 4? So do we get to see so do they have blocks on the periodic table? No, because periodic table is in the ground state. So we basically don't need higher values of L to describe the atoms that we have because those are always in the ground state. And so we are fine with just S, P, D, and F for the periodic table. So these other values of L, then you'd only access in excited states. They do exist. If you are curious about them, the Orbitron website actually has some of those, I believe. So just if you were curious, I like the Orbitron website just because it can show you things like the f orbitals, which we don't test you on, but they exist. It also has g orbitals. So if you were curious what those things look like, you can take a look at the Orbitron website for fun. Again, we don't test on those, but especially not on those shapes. But again, they are real. We use them for excited states. Okay, so I am going to hope that I talked about quantum numbers enough. If not, then come talk to me. This degenerate thing, though, let's talk about that briefly. So all that degenerate means is when we were doing this stuff, and I've got 1s and 2s and 2p, and I'm trying to show these energy levels as keep going up and up and up and up and up. This is for multi-electron systems, which is why there's so many arrows. That's why there's so many arrows. But if we had one electron only, and this only happens when there's one electron, it's weird, I know. If we only had one electron and I was trying to draw the same thing, I'd have 1s, and then I would have 2s, and then I would have 2p on the exact same level. I could have 3s, and then 3p is supposed to be on the same level. And then this is the thing that's weird, is 3d would be here, and then 4s would be on a different level. So the weird thing about degenerate is degenerate energy levels means that those sublevels that are of different energies when you're in a multi-electron system. And that is why when I drew 2s and 2p, 2p is physically up from the 2s, and why 3p is physically higher than 3s, and 3d is physically higher than 3p, because that's true in multi-electron systems. Look at all those arrows. But if you only have one electron, those energy levels are actually degenerate, and that's an excited electron, but that's in an n equals 2, and in a one electron system, all of the subshells are the same energy. Only happens when there's only one electron. It's super, super specific. It's super specific, really weird. But this is also the reason, but the reason why we care about this is the reason why we get to use the Bohr equation at all, because this still describes electrons in a hydrogen atom. It still works. So even though when you get to multiple electrons, it fails, the reason why degenerate is important is because it's the reason why we can use the Bohr equation and why that's not just thrown out the window and fails. It works because if you only have one electron, then your energy levels are degenerate, meaning that every subshell inside of a shell is the same energy only in a one electron system. Teams hates, all right, not teams, it's one note. Okay. One more time. Do we know the atomic line spectrum machine in detail? The machine, no. The atomic line spectra, sure. So we did this kind of already because we were talking about how we go from like high to low and we get energy out. So that's what talking about. So if the just goal is to know what those things are, then I answered that question. But you need to know like how you add energy into electrons to get them excited. No. More clarification on quantization of energy. I don't know what this one means. So usually when we talk about quantization of energy, what we mean is we mean that photons are particles. And therefore you can have one photon with an energy. So again, part of why we can use the Bohr model, part of why we can talk about energy being related to frequency is because energy is quantized and we can talk about individual photons having energy. I hope that's what you wanted, but I'm not confident. The relation between angular momentum and the energy level in Alex. So whenever somebody asks me about Alex, I really want to know what this is from. So I really need a screenshot because otherwise I'm going to go off on random tangents and I'm not sure that's going to be valuable. So I'm going to skip that one. Do you have a method to remember how much energy each subshell can hold, or is it just by memorization? So I think I've answered this one because either we're doing the Bohr model, in which case you're going to calculate it, no memorization, or we're doing things like how many electrons fit in subshells, in which case you're doing quantum numbers, which it's up to you if you think that that's memorization or not. So I don't think this is a, I don't think there's any numbers you're going to memorize for individual subshells. So I know we only did one example, but in the exam review, I did one example of wavelength. I'm going to remind you guys that you have end of chapter questions. The practical use in paramagnetic and diamagnetic. Or practice, maybe means practice in using diamagnetic and paramagnetic. Okay, so we should talk about paramagnetic and diamagnetic. So let's do two examples. Let's do ground state. Ground state means everything's normal. 1s, 2s, 2p. And the question is this diamagnetic or paramagnetic? Diamagnetic. paramagnetic. We do have a tendency to connect diamagnetic and paramagnetic to other things because otherwise this question only has two options. So for example, we would probably ask you, is this diamagnetic or paramagnetic, and how many valence electrons does this have? This is carbon, by the way. So we would actually ask you something like, is carbon diamagnetic or paramagnetic in its ground state, and how many valence electrons does it have? Because otherwise, this question only has two answers. Sorry about that. So diamagnetic means that all electrons are paired. So even though this has two electrons and it has an even number of electrons, this is paramagnetic because it has unpaired electrons. I got two up arrows. That is paramagnetic. In case you're curious, for valence electrons, highest value of N here is 2. I have a grand total of 4 arrows, so this is for valence electrons. So this would be normal for y'all, which is, here is an example, or tell me about carbon and you draw it yourself. So it could just say, is oxygen diamagnetic or paramagnetic in the ground state? And you would need to probably think about this and draw this out. I need a periodic table. Shocker. That is in fact why I have one over here. Okay, so here is oxygen hanging out in group 6A. It has 8 electrons total. So when I'm doing oxygen, 1s and 2 electrons in there, 2s and 2 electrons in there, 2p. I got 4 electrons so far. 1, 2, 3, 4. I still have 2 unpaired electrons. This oxygen is paramagnetic. When you're looking for diamagnetic in the ground state, you are looking for things that are going to have filled subshells. So you do things like your noble gases, things like that. But beryllium, good old beryllium, 1s, 2s. This is diamagnetic. Every electron is paired. So usually your atoms that are at the ends of those blocks are typically diamagnetic. Let me give you one weird example where we would have to draw it for you. Given this excited state, and the question is still diamagnetic or paramagnetic? Diamagnetic, paramagnetic. Or just to make it small. This is the hard one. This is an excited state, so this is not normal. I have broken Hund's rule. But for every up, there is a down. This is diamagnetic. Because for every up, there is a down. So that is what the oddity is of all electrons being paired is. We would have to give that to you, and that is also why you would assume that all electrons are in the ground state. So we always assume all electrons are in the ground state unless we specifically give you more information. But we would have to give you more information. We would have to provide it. That's why at the front it says given. So this is the more challenging one. This is the more challenging option. We do not always ask this because it is weird and fairly rare. But that's another option. So I did that. So I did the 4 quantum numbers and I did the Bohr model equation. Why isn't there an orbital model for F? It's basically just bad in black and white. So I did show off the orbitron for F because you can do it. You just you need some art skills. And even these are a little bit difficult. Like I don't know if it's obvious like what is happening here. Um, because basically this one is particularly is taking this 3D one, but is basically slicing it along the slicing along the Z axis, is actually what's happening in this shape. That's why you can kind of see that other half behind it. And it's a different color. Um, so some of these get really weird and they're difficult to describe. And I can't move this one around, which annoys me. But that's why, is they're bad in black and white. Ah. I did not do a lot of tricks on metric conversions, so this is going to be an office hours question. I also like to do metric conversions, especially one-on-one, because different people have memorized them in different ways. Why SP and D? Why all these wild alphabets? I love this question and not other things. I'm just going to put the word history here. There's a longer story involved in that, and we can talk about it if you want. But it's historical as why it's SPD and F. The other one I do want to address here is one that has nodes. I'm just going to remind you guys that we do not test on nodes. So I think that they're kind of interesting, but we don't test on those, just so you know. Um, do d orbitals always have two planar nodes? No. One of the shape actually has conical nodes. They're in the shape of cones. Conical can happen. Conical can happen too. Does the value of m sub l affect the planar nodes? It's not the value of m sub l that affects the nodes. It's something different. It's the value of L that affects the nodes. Stick to the value of L that affects the nodes. But this is why there's calculus that we're not covering. I'm just gonna put calculus involved. It's a good question though. Anyway, in case you're curious, there's an upper level class. We would just refer to it as P-Chem because the P stands for physical chemistry, and you get like a whole semester of quantum mechanics. It's great. You can actually do a lot more things involved because so much more. There's so much more to chemistry. We just can't do it all. What are the things we have to memorize, specifically charts and formulas? Oh God, I have no idea. I'm just gonna say metric conversions. So you definitely have to memorize those. But there's also that like average atomic mass. Nobody asked me about average atomic mass. So you need to know how to do that. Poop. I don't know. I'm so sorry. Anytime anybody ever asks me what are all the things we have to memorize, my brain just freezes. Because I'm terrified I'm gonna forget something. So I am just gonna put and more. Um, do we need to know the double slit experiment, like the experimental setup? No. Why do Kraft's centrosity localize in stationary waves? So you should know what stationary waves are because stationary waves are how electrons exist in atoms. So you should be able to connect stationary waves to the Schrodinger model, because that is important. The fact that electrons have wave properties, that electrons are waves, and the way that you don't get constructive and destructive interference inside of atoms is because the electron wave is a stationary wave. Is the Schrodinger equation going to be on the exam? I'm going to put conceptually yes. Conceptually yes. Because quantum numbers are all from the Schrodinger equation. But you don't calculate the Schrodinger equation unless you count quantum numbers as calculating the Schrodinger equation, which it's not really because the Schrodinger equation is calculus, but all the quantum number stuff is out of the Schrodinger equation. So maybe. So I'm just gonna say yes. Um, can you basically have an L value that goes so high that you run out of alphabet? Um, I'm sure there's an answer for this. I'm just gonna put I have to look that up because I don't know. Fascinating question, but I don't actually know. So how will we test on the subjects? I am just gonna cheat and refer you guys to the fall 24 exam and take a look at that and see if you have questions. It's very difficult for me to outguess the creativity of my colleagues. Um, so I have some answers for this also on the workshop that I've put out. But again, the exam has 5 different authors, so I will never be able to write questions like everybody else. You got to help me out with what quantum theory, which one you're talking about in there. Because that to me means all of chapter 3. And so I personally need more specifics because I'm not quite sure. Um, okay. So better with quantum numbers, practice, and I would look at more options. So basically what I mean by that is I mean peer tutoring, and I mean reviews, and I mean SI, and I mean end of chapter. I would look at more different material. I would hope that the names combined chemicals. Naming is in chapter 5, which is exam 2. So one of the things I did have this one on here for a reason. Your knowledge checks will ask you questions about anything you've ever gotten right. So if you got questions correct from your initial assessment, your knowledge check will remind you about those topics, even though we haven't covered them yet. Okay, so it's after 8:45. I need to leave my house at 9 a.m. and I don't know if you can tell from this picture, I'm not ready to do that yet. So I am sorry that I didn't get to all of these. If I have time, I will do another follow-up video. I will probably not have time though. So this is the time where anything else you guys want to know, do come ask. There are lots of opportunities. You can also send me an email, and I am sorry that I didn't get to everything, but time is of the essence, and I got to leave my house in 14 minutes. Have a wonderful day. Good luck on the exam. Don't forget to find a way to eat breakfast. The exam starts at 10 a.m. The dining hall opens at 10 a.m. You can't go to the dining hall for breakfast. So do make sure that you have a way to get breakfast the morning of the exam if you want. Some people don't eat breakfast and they can function just fine. This is a know yourself better question. Good luck. You can do this.